Here we have connected particles. We have some assumptions. When you are dealing with connected particles, there are some assumptions which we make. The first one is that the strings which are involved are always taken to be inelastic. That we have that their length is constant. They do not change because of application of the force, and they are also considered light. That means that we don't put into the consideration their weight. We don't consider their weight because they are considered light. When the surfaces are said to be smooth, this is what we have: no resistance to the motion of the body across it. So when a surface is said to be smooth, it offers no resistance to the motion of a body across it. That's one thing you need to take note of. And then we have some note. A string connected to two masses in motion is in a state of tension, and the string exerts forces on the masses equal to the tension at its ends. For a smooth pulley, the tension is the same on the two sides of the pulley. We shall look at this note and shall understand it more when we come to the examples. This one is an example which can help us to understand the thing properly. We have that a body of mass 3 kg rests on a smooth horizontal table. This body is connected by a light string which passes over a smooth pulley at the edge of the table to another body of mass 2 kg hanging freely. Find the acceleration of the bodies and the tension in the string. I hope you can imagine what is happening here, and I guess you can set up a diagram to facilitate your write-up of the solution. I'm going to get you that diagram. Here it is. There it is. We have a body of mass 3 kg resting on the table. There it is. This is connected by a light string which passes over a smooth pulley. There it is, at the edge of the table, you see, to another body of mass 2 kg hanging freely. So this one is how we can analyze that question. That's the analysis of that question. Now if I look at the acceleration, shall be in that direction like that. It is the same acceleration, because as this one is moving, the whole system will be moving downwards like this. So that is what we have. So we shall look at the forces acting on each body. You see this word, smooth horizontal table. So there is no friction involved at this point here. So the resultant force is only this T. So for motion of this one, of the 3 kg body, we have that T is equal to 3A, because the mass involved here is 3 kg. So we look at, actually what we do, we look at the forces on individual, we look at the forces involved, the forces acting on each particle. So the forces on the 3 kg body, tension, no resistance, so the resultant force is the tension, is equal to the MA, which M is the mass of the body involved, so we have 3A. Then we look at this other, actually there is no vertical motion, so we have that R is equal to 3G. That one is also there, but they don't want us to find that R. Then we look at this one here for motion of the 2 kg body. It is with this type of motion, the way we have this acceleration, it means that the weight is bigger than the tension. So we have 2G minus T equaling to 2a, the forces acting on this one. So we have, if we solve this one and that one, we have that this is my equation 1, this is my equation 2. We have that 2g minus 3a is equal to 2a, because the t is the same as 3a. So we have that 2g equal to 5a, implying that a is equal to 2 over 5 times g, that is in meters per second squared. That is the acceleration. When you get that acceleration, we can actually calculate it, and it is 3.92 per second square. That is when we substitute for the value of g, which is 9.80 meters per second. We shall have this value here. Then if you are to get the tension, you can use equation 1, t is equal to 3a. So this one is 3 times 2 over 5 g, which is equal to 6 over 5g. And the tension here is going to be 11.76 newtons. That is what we have there. That has been example 1. I hope you understand it. Example 2. Particles of mass 4 kg and 2 kg are connected by a light string passing over a smooth fixed pulley. The particles hang freely and are released from rest. Find the acceleration of the two particles and the tension in the string. We need some bit of a diagram to help us solve this problem. This diagram can help us solve the problem. These are the particles they are talking about. This one has 4 kilograms and this one has 2 kilograms. Those are the particles of mass, are connected by light strings. Now you remember, light, their mass is not supposed to be taken into consideration, their weight, passing over a smooth pulley. Smooth pulley means that the tension on both sides should be the same. That is, it's the same story with even the first question. This tension is like here, T, the tension here is the same as the tension here, because they are existing on both sides of a smooth pulley. So the same applies to this. The tension here is now some people may wonder, where is the direction of the tension? Tension is relative. It depends on which object you are putting into consideration. If we are, for example, talking about the pulley, relative to the pulley, the string is the tension in the strings are acting in those directions because they are tending to pull the pulley downwards, the tension in the strings, because of these forces down here. However, when it comes to these two forces, like for this 2 kilogram mass, the tension is acting in the upward direction because it is trying to move it upwards. While according to in reference to the 4 kilogram force, as the weight is acting downwards, this one is now supposed to push the body upwards. So that is how we shall get the resultant as 4g minus the upward tension. So relative to this 4 kilogram body, the tension is acting upwards. That is what we have as far as tension is concerned. Now what we do, we are going to use the fact that this one you can write it. We are going to assume that T is the tension, and we are going to use the fact that F is equal to MA. And now when you look at this one, assuming this form of motion, assuming acceleration like that, it is just like that. This one goes up like this and this one goes down. So it is the same acceleration. This one pulls down and it moves this one. They move together because they are connected. So using F equal to ma, consider motion of the 2 kilogram body. If you consider that, since the body is moving upwards, the tension is greater than this one here. So I have that T minus 2G is equal to ma. Actually, it's not just ma, it is equal to 2a, because the mass involved is that one of 2 kilograms. Then consider motion of this one. Since this one is moving downwards, the body is moving like this. So we have that 4g minus t is equal to 4a. That is also what we have there. We need to solve the two equations. We can solve them. Maybe we can say that from equation 1, t is equal to 2a plus 2g. Substitute that in equation 2. 4g minus 2a plus 2g is equal to 4a. This one is 4g minus 2a minus 2g equal to 4a. The a's which we are going to have here, we are going to have 6a equaling to 2g, such that a is equal to a third of g, which is a third of 9.8, and the a 3.27 meters per second squared. With that as the value of a, we can get t from still here. It is equal to 2 times a third. This one is times a third of g plus 2g. This one is 2g over 3 plus 2g, where we shall get 8 over 3g newtons. And we can solve that t, upon putting g, the value of g, shall get 26.1 newtons. I hope you are following this. Just a matter of resolving this. Look at the forces acting on this, look at the forces acting on that, and then solve the equations, and voila, you are there. Two particles of mass m1 kilogram and m2 kilogram are connected by light inextensible string passing over a small smooth fixed pulley. Find the resulting motion of the system and the tension in the string. So we have this system of particles. Let us make some bit of a diagram to help us solve this problem. This diagram can help us solve the problem. Now, as m1 moves downwards with an acceleration a, this one shall be moving upwards with acceleration a still. The tension is the same on both sides, because this one is a smooth pulley. We are going to make that, to assume that we are going to make some supposition. Suppose m1 is greater than m2. We can make use of that. They said find the resulting motion of the system and the tension in the string. So we have that one. We are going to get the acceleration. That is what we are going to get. So for m1, first of all, for motion of this one, since it is moving downwards, m1 is greater than t. So I have m1g minus t is equal to m1a. Call that equation 1. Then for m2, we have that for motion of this one, since it is moving upwards, we have a tension bigger than the other one. So tension minus M2G is equal to M2A. That one is equation number 2. Get equation 1 and we add it to equation 2. When you do that, we shall be eliminating T. So we have M1G minus M2G equal to M1A plus M2A. And this means that A is equal to M1 minus M2 over M1 plus M2 times G. That one is the value of the acceleration. Let us use the equation 2, that T is equal to M2 into A plus G, which is equal to M2. Now what we have as A is M2, it is M1 minus M2 divided by M1 plus M2 times G, then plus another G. That's what we have. We shall have further that this is M2. We can, this one is a square bracket. So we have LCM and we have M1 minus M2 G plus this one is M1 plus M2 G divided by M1 plus M2. And we further have, when you work out the upper one here, the numerator is minus M2 and plus M2, and shall have simply M1, that is M2 out there, and inside we are going to have 2 M1, because the M2s, we have negative M2G and positive M2G. So I have 2 M1G divided by M1 plus M2. So the tension is 2 M1 M2 times G divided by M1 plus M2. That is in newtons. So the ensuing motion bears an acceleration which is this one, that is in meters per second squared, and the tension, it creates a tension given by this expression in the strings. And we may be interested in getting the reaction at the pulley, reaction on the pulley. If you are to get the reaction there, we shall have this one as the pulley. You have forces downwards, there is tension, and the tension, there will be a reaction in the upward direction. So the reaction R is given by 2 times T. It is 2T. So the reaction on the pulley is going to be 4 M1 M2 G divided by M1 plus M2. That is in newtons. Reaction on the pulley, that is what we have there. I think we have talked about the motion of the system. We have got the acceleration, we have got the tension involved, the reaction on the pulley. That is what we can say about that problem. Here is another example. A mass M2 kilogram is placed on a smooth horizontal table and connected by a light inextensible string. Inextensible is the same as inelastic over a small smooth pulley at the edge to a mass m1. This one is supposed to be m1 kilogram, m1, as in this one is a subscript, m1 kilogram hanging freely. Find the acceleration produced and prove that the force on the pulley is m1 m2 g root 2 divided by m1 plus m2. We need to set up some bit of a diagram to help us get this problem solved. This diagram can help us achieve our aim of solving this problem. We have the m1 on the table, the m2 on the table is there, passing over a smooth pulley which is here. You have the string and then passing over another m1 hanging freely. It is upon you to get the question, understand it, and set up a diagram that can help you to solve that problem. As you can see, the diagram, I'm just drawing it. It is not supposed to be part of the question. So you are supposed to set up that diagram yourself by understanding the question. Of course, it starts from understanding the question, because once you do not understand the question, you can't solve the problem. We are going to consider motion of each one. Now, for motion of m2, we have that t is equal to m2a. We are using the fact that f is equal to ma. So when we look at this one, it is a smooth horizontal table. So there is nothing like a friction opposing. So the resultant force acting on the thing is t minus 0. So it is just t, which is the one which is equal to now ma. So t is equal to ma. That one is our equation 1. Then we look at motion of this one, motion of the m1. It is moving downward, so mg, the weight of m1, is supposed to be greater than the tension. So we shall say that m1g minus t is now equal to m1 times a. Call that equation number 2. We can have equation 1 plus equation 2, because by doing that we shall be eliminating the value of t, such that m1g is equal to a into m1 plus m2. We are adding this one plus that. Factorize out to a, then you have the sum of the masses. A is equal to m1g divided by m1 plus m2. That's the value of the acceleration. And now the tension is m2a. Tension from equation 1, tension is equal to m2a, which is equal to m2 into m1g divided by m1 plus m2. That is what we have there as the tension. That one is in newtons. And they said prove that the force on the pulley is this. Force on the pulley, you look at that one. The forces acting on the pulley are like this. We have tension there and then tension there. So we have T and T. And these are two forces acting at right angles. So the force on the pulley, is equal to, maybe I can call it, let me call it F is equal to square root of t squared plus t squared, which is equal to square root of 2t squared, and is equal to t square root of 2. So we have t times root 2. But what is it? It is m1 m2g divided by m1 plus m2. then square root of 2. And precisely I think this is what we have. We are just getting from the fact that the force on the pulley is the resultant of two forces T and T acting at right angles to one another, which can be got by getting the square root of the square of the two forces. And I think precisely this is what we have, as it is what they put there and it is what we have just got there. That's it. We have a car of mass 900 kilogram. A car of mass 900 kilogram tows a trailer of mass 600 kilograms by means of a rigged tow bar. The car experiences a resistance of 200 newtons and the trailer a resistance of 300 newtons. If the car engine exerts a forward force of 3 kilonewtons, find the tension in the tow bar and the acceleration of the system. Roman 2. If the engine is switched off and the brakes now apply a retarding force of 500 newtons, what will be the retardation of the system, assuming the same resistance apply? What will be the nature and magnitude of the force in the tow bar? We need to make some bit of a diagram to help us. We need some facilitating diagram in solving this problem. This diagram is the one that can illustrate whatever is there. This is the car, this is the trailer. When they talk of trailer, don't think of these huge things. They are those small things that just a carriage that comes with that can be put behind the car. It is also referred to as a trailer, not in that huge thing. Because somebody may say, now the car is bigger than the trailer. Yes, we are not talking about the other trailer, but just that small carriage behind which they put behind there. So a car of mass 900. Having a mass of 900 kilograms means a weight of 900 times g times gravitational acceleration. And the mass of the trailer is there. This is the tow bar. There is some bit of tension there. There is tension with respect to the car. The tension is acting backwards, because as the car is moving forward, the tension is pushing it backwards. You see? So, and when you have the tension with respect to the trailer, it is the tension, the bar with the tow bar that is pushing it forward. So the tension with respect to this one is pushing forward. That's why you are seeing this one there and that one there. The forward force 3000. This one is 3 kilonewtons. Kilo means 1000, kilonewtons. So 3 kN means 3000. 3 times 1000. They said find the tension in the tow bar and the acceleration of the system. We have some resistance forces. The car has a resistance of 200. It is there. It is reflected there. While the trailer has a resistance of 300 newtons. It is also reflected there. So we are going to look at the motion of each of those components. Look at motion of the car. Start with the car. For motion of the car, we have the tractive pull 3000 acting forward. This one. Subtract the forces in the opposite direction. So we subtract the sum of T and 200. That should give us MA. Which mass are we considering? The 900 kilograms. So this will give us 900 A. Remember, both bodies are accelerating with the same acceleration because they are connected. This one and that one will get us 2800 because this one is a minus, then minus T equal to 900 A, where we can say that T is equal to 2800 minus 900A. I'm preferring to call that equation number 1. Then we'll also look at motion of the trailer. For motion of the trailer, now for the trailer, it is we're looking at motion in that direction. So we have T minus the resistance force, which is 300. It should give us 600 times A. And for this one, T is equal to 600. Maybe I can say it is equal to 300 plus 600A. That is equation number 2. What we are going to do here, since this is T and this is T, we are going to equate the two and we get the acceleration. The question is asking for the tension in the turbine and the acceleration of the system. So we are going to first of all get the acceleration by equating the two equations. We have 2800 minus 900A is equal to 300 plus 600A. This one is 2500 equaling to 1500A, such that A is equal to 2500 divided by 1500. 2 zeros go by 5. I have 5 over 3. 5 over 3 meters per second squared. That is the acceleration. One whole number and 2 over 3 meters per second squared. Then the tension T, we can use equation number, let's use equation number 2. So T is equal to 300 plus 600 times 5 over 3, which is equal to 300 plus this one is the sum 200 then times so this is 1000, getting us 1300. That one happens to be the tension produced there. That's the tension produced in the turbine. Then Roman 2 is saying that if the engine is switched off and the brakes now apply a retarding force of this, so the condition we are going to have there is a case where, maybe let me refresh this thing first of all. You're going to excuse me, the space is actually this one is now Roman 2. This is the scenario we have. We are having that the forward force has been is normal because the engine is switched off. Once we switch off the engine, there is no more force pushing this thing forward. But that one does not mean that the car is going to stop immediately. It is going to continue moving, but with some bit of a retardation because there is a resistance force. That they're even applying the brakes and we are having another opposition force which is being set up here, a resistance force of 500. On addition to the other two, there is on the other 200 newtons. So they said what will be the retardation of the system, assuming the same resistance applied. I'm talking about the same resistance of the first case, the 200, the 300, and now they have applied another. The brakes are applying another 500. So we shall consider motion of the car still. Consider the car. Motion of the car. We have, if we consider the motion of the car, we have 0 minus, I can say 0 minus T plus 200 plus 500 is equal to 900A. Let's take the T the other side, and we have that T negative 700 plus 900A. Shall call this one equation number 1. We also consider motion of this one. That one there will not be, there is not much here. We have for trailer, we have T minus 300 is equal to 600A, where we have that T is equal to 600A plus 300. Call that equation 2. We can add the two equations, and this one is equation 1. When we add the two equations, we shall have negative 700 minus 900A equal to 600A plus 300. This one goes there, and we shall have negative 1500A is equal to 1000, such that A itself is equal to negative 10 over 15, which will get us 2 divided by 3 meters per second squared in the negative. This one means a retardation. So retardation, if I write the word retardation, shall have that retardation is 2 over 3 meters per second squared. When you're writing retardation, you again do not put the negative, because retardation means negative acceleration. So the retardation itself is 2 over 3. If you are to use this retardation in the formula where you have A, you're going to have it as negative, because it is a what? A retardation. So we are having a retardation of 2 over 3 meter per second squared. From we can use the first, let's just use the second equation. T is equal to 600 times 2 over 3. This is negative still. Then plus 300. You have that T is equal to negative 400 plus 300, getting us negative 100 newtons. They want us to tell they were like what would be the nature and the magnitude of the force in the tau bar. That is the T. So we are getting that T is negative 100. So this one is no longer just a tension. This force is not a tensile force. So once the car applies the brakes, this force is not going to be tensile, because there is some bit of compression. This one is going to get closer to this one, and there will be some bit of a thrust. So we are going to say that there is a thrust of 100 newtons. That one is, you can call it a compression. There will be some bit of a compression. It is no longer a tensile force, but a compressional force. So there is a thrust of 100 newtons in the tau bar.